Hey guys, so today we're going to learn about interest formulas and growth and decay formulas. Compound interest is interest computed on your original investment as well as on any accumulated interest. The formula A equals P plus PR equals P parentheses 1 plus R parentheses. Suppose the sum of money, called the principal P, is invested at an annual percentage rate R in decimal form, compounded once per year. Because the interest is added to the principal at the year's end, the accumulated value is A. Compounded semi-annually is compound interest that is paid twice a year. Also, you could write this as N equals 2. When compound interest is paid 4 times a year, the compounding period is 3 months, and the interest is said to be compounded quarterly, which is the same as N equals 4. In general, when compound interest is paid N times a year, we say that there are N compounding periods per year. The formula A equals P parentheses 1 plus R parentheses T can be adjusted to take into account the number of compounding periods in a year. If there are N compounding periods per year in each time period, the interest rate is R over N, and there are N T time periods in T years. This results in the following formula for the balance A after T years. Continuous compounding is where the number of compounding periods increases infinitely. Okay, so if you look at this formula here, N over R times RT equals NT. Let H equal N over R. As N approaches infinity, H approaches infinity. As H approaches infinity, by definition, parentheses 1 plus 1 over H raised to the H power equals E. So that leaves us with our formula for continuous compounding is A equals PE to the power of RT. So here we have an example. You decide to invest $8,000 for 6 years, and you have a choice between 2 accounts. The first pays 7% per year, compounded monthly. The second pays 6.85% per year, compounded continuously. Which is the better investment? The solution: the better investment is the one with the greater balance in the account after 6 years. Let's begin with the account with the monthly compounding. We use the compound interest model with P equals 8,000, R equals 7%, which equals a decimal of 0.07, and N equals 12. So we get the 12 from monthly compounding means, 12. Compounding per year, and T equals 6. Okay, so our formula A equals P parentheses 1 plus R over N equals, parentheses raised to the NT power equals 8,000. So we're just plugging in numbers. So for R, we're going to put 0.07 N 12, and then N again for the power of N 12, and the power of T 6. When you do that, you approximately get 12,160.84. The balance in this account after 6 years is 12,168.84 cents. For the second investment option, we'd use the model for continuous compounding with P equals 8,000, R equals 6.85%, which as a decimal equals 0.0685, and T equals 6. So now you're going to use the formula for the continuous compounding, which is A equals PE to the RT power. So again, you're just plugging in numbers. P would be 8,000. Your R would be your percent, or 0.0685, and your T would be your time, which would be 6. When you plug that in your calculator, you get $12,066.60. The balance in this account after 6 years is $12,066.60, slightly less than the previous amount. Thus, the better investment is the 7% monthly compounding option. Okay, exponential growth or decay. With exponential growth or decay, the quantities grow or decay at the rate directly proportional to their size. The mathematical model for exponential growth or decay. Okay, so this would be if k is greater than 0, the function models the amount or size of a growing entity. A0 is the original amount or size of the growing entity of time t, which equals 0. A is the amount of time t, and k is a constant representing the growth rate. If k is less than 0, the function models the amount or size of a decaying entity. Okay, A0 is the original amount or size of the decaying entity at time t equals 0. A is the amount of time t, and k is a constant representing the decay rate. Okay, so let's do an example. In 1970, the U.S. population was 203.3 million. By 2010, it had grown to 308.7 million. So the first question, find an exponential growth function that models the date for 1970 through 2010. Second question, by which year will the U.S. population reach 335 million? Okay, to solve this problem, you're going to use the growth or decay formula. A equals A sub 0 E raised to the kt power, So, use the growth model with A sub 0 equals 203.3. When t equals 40, A equals 308.7. Substitute these numbers into the model. Isolate the exponential factor by dividing both sides by 203.3. We also reverse the sides. Take the natural logarithm on both sides. Simplify the left side using the log of e to raise to the x power equals x. Divide both sides by 40 and solve for k. Then use the calculator. Once you do that, you should get an answer of 0.01, approximately 0.01. Okay, to find the answer to question B, you're going to use the 1% growth rate that you found in question A. You're going to model this is the model from part A. Substitute 335 for A. Divide both sides by 203.3. We also reverse the sides. Take the natural logarithm on both sides. Simplify the left using the logarithm e raised to the x power equals x. Divide both sides by 0.01 and solve for t. Then use your calculator. So you're going to get approximately 50. Because t represents the number of years after 1970, the model indicates the U.S. population will reach 335 million by 1970 plus 50, or in years 2020. I hope this video helps.